Do you hear me? It's time to start this parallel session. So the first speaker is Aditya Parki. So are you ready?
Yeah, let me just share my screen.
So the time is for 20 minutes. So please start.
Okay. All right. Thank you, everyone. Thanks for the introduction. So today I'm going to be talking about exploring the COSIM dark sector, and this is work that's been going on in collaboration with John Beacom, Yuri Smirnov, Linda Zhu, and Bei Shou. So just to get started, I'm going to be talking about thermal relic dark sectors. So for the purposes of this talk, when I mention thermal, what I mean by that is a sector that is internally thermalized, so it's all at the same temperature. And this had to have happened at some cosmological epoch over the course of the universe's history. And this can either happen via self-interactions within the dark sector or interactions with the standard model, or both. There's a plethora of mechanisms, and in turn, there's also a lot of potential observables. And in particular, if we focus our attention to thermal relics, they in particular leave imprints of these various high energy processes in low energy observables. So the purposes of this talk, when I say thermal relic, I mean a dark sector species whose present day number density is set by number changing interactions, either in the form of freeze out or freeze in processes. And since these change the number of dark matter particles, they essentially help set how many, the density of dark matter that we have today. The thing to point out with thermal relics are first that they're very generic, and second, they also happen to be fairly predictive. So with that in hand, we can explore the thermal relic zoo that we have. So the canonical example of thermal relics was always the WIMP, the weakly interacting massive particle, where dark matter annihilation in the form of chi-chi going to two standard model particles set the relic abundance. And obviously the WIMP miracle was when we choose a weak scale cross section and sort of order one numbers, we end up getting the correct relic abundance for a cold dark matter species. But the thing to point out is that there's various other possibilities. And these include things like warm dark matter, where the decoupling happens when the dark matter is still semi-relativistic and it can still scatter with the standard model. We can have decaying dark matter, where instead of two dark matter annihilating, we can have one decay into two standard model particles. We can have things like cannibal dark matter, where you have 3-to-2 number changing self-interactions, as well as other things like SIMPs, forbidden dark matter, elders, kinders, or just sort of more general number changing interactions through a richer SIDM phenomenology. So with that in mind, we can look at sort of what mass ranges we kind of expect. So if we take the canonical WIMP example, the expectation is to have dark matter in the GeV to TeV range for their masses. And as we see here, and it's a slightly old plot, but if we look at the bulk of the constraints, they've mostly pushed down within this mass region towards the neutrino fog. But if you consider new mechanisms, so for example, we can consider something like the SIMP, where you can have 3-to-2 processes. If you look at the velocity weighted cross section, it scales roughly like alpha cubed over n to the fifth. And if we want to get the correct relic abundance of dark matter today, then the velocity weighted cross section times the mass squared should go like 10 to the 8th inverse GeV cubed. So the natural expectation with sort of order one couplings would be an MEV to GeV range dark matter mass, which is sort of in this sort of top left region of this constraint plot here. And we see that there aren't too many experiments that have really pushed down to the neutrino fog in this region. So the main thing is that the standard direct detection experiments that we have are often not the best suited to search for these new mass ranges. So if we look more specifically at the COSIMP idea, the COSIMP dark matter paradigm basically is a 3-to-2 process that involves both the visible and the dark sectors. And it's a number changing process for the dark matter in that you start with 2 dark matter particles and 1 standard model particle, and you end up with 1 visible and 1 dark sector particle. And The other thing is that it's a strongly interacting theory, so you can easily lead to kinetic equilibrium with the standard model. And since we have, in essence, a spectator standard model particle, you can basically prevent the dark sector from overheating, which is one of the typical issues that you have with sort of 3-to-2 interactions just in the dark sector. Um, Within this paradigm, you typically expect masses in the keV to MeV-ish range. And as we saw earlier, standard direct detection experiments are not the best suited to sort of probe this region. So we can take an effective field theory approach to it. And if we just consider cosine freeze out, the cross section will scale as 1 over the cube of the dark matter mass. And it also scales is inversely proportional to the baryon to photon ratio and the current dark matter density. So if we consider a scalar dark matter chi that's coupled to non-relativistic electrons, then it'll be coupled through this operator here, chi cubed del bar. And since we're coupling to non-relativistic electrons due to the inherent chirality flip that's required, you actually need a mass insertion, electron mass insertion. And so this is naively a dimension 7 operator here due to this mass insertion. If we look at the cross section that you get from something like this, it roughly scales like the square of the electron mass divided by the dark matter mass times cutoff to the 6th. So if we require, a 0.1 MeV dark matter that still sets the correct relic density through freeze out, then we end up getting a cutoff that's order MeV. So the main takeaway here is that you have a low cutoff, and therefore it's important to start considering UV completions. So, the simplest completion that we can consider is just a scalar model. Here we have a scalar dark matter chi. Its interactions are mediated by another scalar phi. And this phi couples both to the dark matter chi through a quartic interaction, as well as the leptons through a phi LL bar type coupling. And the reason that these are the lowest dimension operators you can write down is because there's also an inherent Z3 that's imposed on the dark sector where chi is charge 1 and phi and all the standard model particles are uncharged. Now, within this model, we make chi stable by taking its mass to be less than phi. So phi in principle can decay, but chi will be stable. So you have a stable dark matter species. And the free parameters in this model are the two masses, as well as the couplings of phi to both the dark sector and the visible sector. And just to sort of have a lamppost of where we're going to be looking, the approximate parameter space that we'll be interested in will have small coupling between 5 to the standard model, a order 1-ish coupling, so sort of strong coupling in within the dark sector, and masses in their 10-ish keV range. So one thing that I sort of brushed under the rug, and it's important to point out, is that the coupling that I wrote down on the last slide is actually not SU2 invariant. So the scalar lepton coupling, Lorentz invariance would require the leptons to have opposite chirality. So in principle, that phi LL bar type coupling that I had written down should actually have a Higgs insertion, and it should really be a phi H LL bar coupling. So I've been saying that I have a UV complete model, but here I have a dimension phi operator. So what we really need to do is actually figure out a way to generate this from dimension 4 or lower dimensional operators. So one way of doing this is to basically introduce an additional heavy spectator vector-like fermion E. And this E will couple via both H L bar E and phi E L. And then what you can do is first you can integrate out this E. This will help generate this dimension phi H LL bar type coupling. And then once you break electroweak symmetry and put the Higgs on its bed, this will reduce into an effective dimension 4 operator like the one that I wrote on the previous slide. So the upshot of this construction is first you preserve SU2, which you are required to do by the standard model gauge group. You avoid direct neutrino couplings, and because essentially this vector-like fermion doesn't really play an important role in any of the cosine phenomenology, you can essentially make it heavy, and this will help you reduce precision Higgs decay constraints, as well as Higgs mixing and things like that. So essentially, the upshot of this is that you can avoid some of the standard constraints that you can sort of expect. But there are other constraints that are not so easy to evade. So the first class of these are cosmological constraints. The first of them is just late thermalization and ineffective. So anytime you have a light dark matter species or anything that is relativistic in the early universe, it'll contribute to the radiation energy density. And specifically at two different epochs in the evolution of the universe, we know that ineffective is very well constrained. The first is at BBN, and the second is at CMB. So to help avoid these constraints, the first thing that we need is that the thermal production of this dark sector needs to be inefficient until after BBN. This way, you'll basically won't have a relativistic particle species at BBN, and therefore you don't have any contribution to ineffective. And then the second constraint this imposes is that freeze out needs to occur before the CMB is set, and therefore that kind of gives you a window where these cosine type processes will be active. The next thing is relic abundance. Basically, we want this to also set the correct amount of dark matter that we have. So in principle, anything that can change the number of any type of process that can change the number of dark matter species can play a role in the relic abundance. So in particular, some of the main processes that we have are chi-chi goes to chi-phi and 3 chi's go to a pair of electrons, but this is kinematically shut off because chi is lighter than both phi and the electron. We also, just as an assumption, will take that the 4 to 2 dark sector process is just suppressed. So that way you can isolate the dominant contribution to just be from cosine type processes, which are chi-chi E goes to chi-E and chi-chi gamma goes to chi-gamma. Then you have two other classes of constraints, which are astrophysical and terrestrial constraints. So within astrophysical constraints, you have stellar cooling constraints. And basically what this implies is that anytime you have a light dark sector particle, it can be produced within the core of stars. And if it escapes, it can basically overcool the star. So to avoid this, what we require is that either the dark sector particle needs to be so massive that it won't be produced in the cores of these stars in appreciable quantities, or they'll decay before escaping the actual star, and therefore it'll deposit all of its energy back within the star. In particular, you have sort of two constraints. One are red giants and the other are horizontal branch stars, and they essentially tell you that depending on sort of which one you believe and in how rigorously these are modeled, it tells you that the lifetime needs to be on the order of 200 or 2 seconds, and the temperature needs to be, or the mass needs to be heavier than 20 or 2 keV. You also have self-interactions, which essentially either at tree level, you can have 3 to 3 interactions via this diagram, or at loop level, you can have 2 to 2 interactions via this diagram here. And this will essentially change the morphology of galaxies and their dark matter distributions within galaxies. And then finally, at the terrestrial level, you have lepton G-2 constraints, where the dominant constraint on the coupling between phi and the standard model comes from this. And then finally, elastic scattering, you can have chi electron going to chi electron, and this is something that can be mediated at 2 loops. So with all of these constraints, we can look at the money plot. So the things to point out here, this is the various constraints plotted as a function of the mass of the dark matter and the coupling of phi to the standard model. So in the top right, this part is ruled out by BBN constraints. Up here, you have G-2 constraints from the muon, and down here, these are G-2 constraints from the electron. So the electron constraints are generally stronger. For light dark matter, you have constraints, parameter space ruled out by horizontal branch stars as well as red giant stars. And then finally, these xenon 1-ton constraints are up here with various values of the coupling between phi and the dark matter. And then finally, these black lines here are just the correct relic abundance, as well as some 1 or 2 sigma bands on the sides. So, and the sharp corner here is basically just where the SIMP process, the 4 to 2 process that we had neglected, in this region of parameter space, this is where this essentially actually takes over. And so this becomes the dominant, starts to dominate over the COSIM processes. And that's the reason why you get this sort of sharp turnoff here. And the other thing to point out is that the xenon 1-ton excess can marginally be fit for about 40 keV dark matter. So just to briefly conclude, the main takeaway that I want to point out is that first, there are still viable thermal relic models. So even if the WIMP is dead, you have other thermal relic models that are viable. COSIMs can give us keV-ish mass thermal relic dark matter, and it can also help alleviate the problem of overheating the dark sector, which is the standard issue with 3 to 2 type processes just purely in the dark sector. This COSIM paradigm is not just restricted to scalars. I didn't have time, but there is also a fermionic realization of the scenario that we're working on. And finally, the main takeaway is that there is also a rich phenomenology that's associated with these new mechanisms. So it's crucial to help push this direct detection towards lower masses, which has been going on recently on the experimental side. So thank you.
Okay, thank you for a good talk. And we have now time for questions. Okay, this Takehiro, please ask.
I just clap hands.
So, is there any question?
I have a question. I'm Hyunmin.
Yeah.
Yes.
Please.
Yeah. What about indirect bound on this COSIM dark matter, like a CMB or some? I mean, through you still have a 2-2 annihilation channel active in the small temperature. Does it change its CMB recombination, for instance?
So the 2 to 2, so you're worried about 2 to 2 annihilation of chi going to what? So the phi, the scalar phi that you have is heavier than chi. So if you have any type of process like that, it's going to be suppressed because it'll be, you'll be accessing the exponential tail of the Boltzmann distribution, as well as if you had some kind of annihilation into standard model, and then the annihilation into just photons will also be suppressed because the coupling between phi and the electron is small. So you have to essentially pay that suppression. So you can usually CMB bounds because of that.
I see. So in your case, the dark matter mass is smaller than electron mass, so that annihilation into electron positron pair is forbidden.
Yeah, it's forbidden right. It'll be forbidden or just exponentially suppressed. Basically, if you have some high energy enough chi's floating around, but. Yeah, because it's lighter, you don't have to worry.
I now remember. Okay, thank you.
Okay, another question? If not, okay, thank the speaker. And so let's move to the next speaker. The next talk is by Neil Shah, and the title is Real-Time Approach to Vacuum Tunneling. So, are you ready?
Yes.
Please start.
Thank you. Let me share my screen. Let me go to full screen here. All right. Can everyone see my screen and hear me okay?
Yeah, yes, please.
Awesome. Thank you. All right, yeah. Thank you so much for having me here today. My name is Neil Shah. I'm a PhD student at Tufts University, and I'll be talking today about some work that I did with my advisor, Professor Mark P. Hertzberg at Tufts, and a postdoc student at Tufts, Fabrizio Rompinev. And our work focused on the analysis of a real-time approach to quantum tunneling, which I'll talk about in this talk. So here's a brief overview of my talk. So first I'll be talking about the instanton, which is in the literature the standard imaginary time approach to quantum tunneling. Then I'll be talking about the stochastic method, which is this real-time approach. I'll be talking about the results of our paper and ending with some conclusions. Great, so quantum tunneling is a very important and ubiquitous idea in physics. It appears in many different fields of physics. For example, in particle physics, there's the Higgs field, which is, as we know, metastable, and there's some turnover and some high energy scale. In string theory, for example, there's actually when you compactify and you look at some field theory, you actually end up having exponentially many metastable vacua. And in other fields, such as even condensed matter and nuclear physics, quantum tunneling is a very central concept. So whenever you're talking about quantum tunneling, the important quantity that you're talking about is the tunneling rate. That's kind of the very important thing to measure. So in single particle quantum mechanics, extracting a tunneling rate for some system is actually usually quite straightforward. You can just exactly solve the Schrodinger equation and obtain the tunneling rate that way. However, in field theory, the exact solution from the Schrodinger equation is often very prohibitively difficult to obtain. So we often rely on approximation techniques to obtain tunneling rates. So the standard approximation technique in the literature is called the Coleman instanton. It involves a classical solution in Euclidean spacetime. So you can move from Lorentzian spacetime to Euclidean spacetime by doing this Wick rotation, where you move to imaginary time. And if you look at the equations of motion, you're, if you have this O4 symmetry in your system, in the Euclidean spacetime, your field behaves it evolves under classical equations of motion, where the classical equations of motion involve this inverted potential, which you can see here. So the instanton is a very powerful method used to estimate tunneling rates with great success. However, this O4 symmetry is unfortunately broken in a lot of key regimes. One of the most important of which is inflation. So if we can find a real-time tunneling method, we can actually estimate tunneling rates in regimes that don't obey this O4 symmetry, for example, in inflation. So one such method is called the stochastic method. Past work by people like Linda has shown at least parametric agreement between the stochastic method and the instanton. However, recent work by Braden, Johnson, Paris-Ponson, and Weinfertner claimed actually excellent agreement between the stochastic method and the instanton, which was very promising. So you can see here, this is a plot of the results. You can see the tunneling rates on this axis. In the orange is the stochastic method, and the blue is the instanton. There's a very, very good match here. And so we want to explore this method and confirm these and explore these results. So let me just briefly talk about what the stochastic method is. So let's say you have a potential with at least two minima, a false minima and a true minima. So the false minima sits at a higher potential value than the true minima. And you want to initialize your field around the false vacuum. And so you have some fluctuations, and you also want to initialize your momenta, and you have some fluctuations in the momenta. And so you want to draw these fluctuations from the free theory. So you can assume that around the false vacuum, you roughly have the free theory. So you can draw these from this wave function. And you can write down the 2-point correlation functions from this as well. So because we're actually going to be using a semi-classical method, so what we want to do is, since we're going to be doing classical evolution, we want to be able to draw these fluctuations in phi and pi simultaneously. So what we can do is we can use the Wigner distribution to draw these simultaneously in order to set initial conditions. And since we're working in the free theory, the Wigner distribution is positive definite, so we can use it as a joint probability distribution for phi and pi. And so we'll use that to set our initial conditions. And we can place phi in a box of size L with periodic boundary conditions. So this will discretize our K modes and give us some cutoff on the theory. Okay, so we can write down our initial conditions. So that in Fourier space, it's written out this way, where these Fourier coefficients right here are drawn from a Gaussian. And the Gaussian has this width, which is just given by the free theory. So yeah, this is kind of how we set up our initial conditions. And you'll notice we've introduced these fudge factors here, which are essentially used to control the amplitude of the fluctuations. And I'll come back in a little bit as to why we do that. All right, so how do we extract the tunneling rate from kind of all this methodology? The basic idea is we want to prepare a large ensemble of classical fields, and we'll set their initial conditions by drawing from the free theory as we just talked about, and we'll evolve all these fields under the classical equations of motion. The way that we determine the tunneling rate from this behavior is we define some volume average for the field, which I'll talk about in a second exactly what this is. And we want to choose some threshold value t such that a field phi has tunneled at a time t when this volume average is greater than this threshold. So you can imagine that the threshold can be something like the hilltop. So when the classical field has gone over the hilltop, it's kind of tunneled. We'll define the survival rate of the fields, which is given as the number of fields that have not tunneled at a time t. And we say that the survival fraction of this ensemble should go as e to the minus gamma t, where gamma is the tunneling rate. So by fitting the survival fraction as a function of time, we can extract the tunneling rate. All right, so coming back to what that volume average is, it'll depend on the potential we're looking at. So we're looking at two types of potential. We're looking at a periodic potential, which was used in the Braden paper, which essentially has an infinite number of false and true vacua. And we also look at this standard asymmetric double well, which also is just one false and true vacuum. So for the double well potential, the volume average is just the standard volume average over the box. It's just the standard volume average. For the periodic potential, we actually take the volume average of the cosine of the field, and I'll explain in just a second why we do that. Okay, so starting with the cosine potential, it has this periodic form over here. And the nice thing about this potential that this Braden paper uses is that the cosine of phi actually tracks the tunneling. So cosine of the false vacuum is -1, cosine of the true vacuum is +1. So that's why we kind of look at the cosine of the field. And for now, we're going to set these fudge factors equal to each other. And again, we'll see in a second why this is important. Okay, so kind of putting this all together, what do we get? We get, so here you can see the volume average of the cosine of the field for our large ensemble of fields. You can see that while a lot of them don't tunnel, some of them do kind of start to tunnel, and they go from -1 to +1. They go from the false to the true vacuum. You can see a lot of these fields are tunneling. So by looking at the survival fraction of these fields over time, we can extract the tunneling rate. And here is our tunneling rate for our periodic potential versus some parameter that controls the shape of the potential. So you can see here, we actually have set the epsilon to different values. So epsilon equals 1 is the true physical value. Epsilon equals a half is actually what we realized the Braden paper was using. We had noticed that they were accidentally kind of suppressing their fluctuations using this fudge factor of a half. So you can see that when we kind of artificially suppress our fluctuations, we get quite a good match to the instanton as they observed, where the instanton is the solid line and the blue dots are the suppressed fluctuations. But we can see when we set the fluctuations to the true physical value, we get parametric agreement, but certainly not complete quantitative agreement here. So we wanted to see, well, how about, do we always get agreement for every potential as long as we set this fudge factor to a half? Is this like a value that'll work for every potential? So we tried to work with now a double well potential. And here you can see again the same field average of phi over time. You can see you have the same type of behavior, a number of fields tunneling over time. And yeah, and you can see here that we do get agreement when we change the value of epsilon, but it's not 0.5 anymore. We actually get a much lower value, 0.375. And for the true fluctuation amplitudes, we still don't quite see the quantitative agreement. So we wanted to make sure we were accounting for renormalization effects. So we calculated the one loop correction to the mass in 1+1, which you can see is given here. And we tried to work in a regime where the renormalization correction is quite small. So we could kind of effectively not have to worry about it too much. So by requiring this difference between the renormalized mass and the bare mass to be small, we get an upper bound on the cutoff, and we can redo our simulations using these new cutoffs. And we see that it doesn't quite, it still doesn't quite help us give a perfect match. We do get better agreement, but it's not quite exact. And we do still have new fudge factor values as well here. All right, so another thing we just wanted to try was to try, instead of changing both fudge factors for phi and pi in exactly the same way, we wanted to kind of try and change them inversely, as is shown here. With essentially the idea being if they're inversely proportional to each other, you still get a satisfaction of the uncertainty principle. So you can write down the uncertainty principle, which is a function of these fudge factors. And so clearly for the Braden values of the fudge factors, you get a violation of this uncertainty principle. So we tried it for these physical states by changing these epsilon values. But you still see, we still get, the pattern seems to be the stochastic method tends to keep overestimating the instanton rates, where the instanton is shown in black right here. So you still get overestimation overall. And we also wanted to just try this method in single particle quantum mechanics, just to see if kind of maybe we get more success in this in the single particle case rather than the field case. So we looked at this kind of escape potential where we initialize our initial wave function in this middle well, and then the part and this kind of wave function is able to leak out, kind of tunnel through. So we can look at the exact quantum variance in position over time, and we can also do something kind of the single particle analog of the stochastic method, where we can create an ensemble, a large ensemble of classical particles that start roughly in the well, and their initial position and momenta are picked from the quantum theory, from the Gaussian distributions with these variances that come from the quantum theory. And then we can just evolve the ensemble over time and look at the ensemble average and compare it to this quantum variance. And you can see we have some good agreement at first, but there's kind of this divergence over time. So it seems like we're still kind of not getting a great match in the single particle case as well. Okay, so I'll end it here with some conclusions. So the instanton is, as we talked about, an imaginary time approximation of tunneling rates that fails for certain time-dependent backgrounds. Recent work introduced a real-time formalism that claimed excellent agreement to the instanton. We showed that this isn't quite true. We saw that the stochastic method tends to actually over-predict tunneling rates systematically unless the fluctuations are artificially suppressed. But we do have some hope for this method. We're hoping in some future work to be able to develop a prescription for obtaining ideal fudge factors for potentials and be able to just take a potential and be able to spit out what are the fudge factors needed to have the stochastic method give the accurate results. So we're kind of still doing some future work on that. And hopefully we'll have an update about that soon in the future. All right, thank you so much.
Okay, thank you there.
Thank you.
So question time. So anybody?
I think Oshi.
Yes, I have a few questions.
Sure.
May I?
Yeah.
So now since you consider stochastic fluctuations, so I'm wondering where you took into account the quantum mechanics in this method.
Yeah, so that's a great question. So the quantum mechanics really is only in the initial conditions. So basically when we're picking these initial conditions, we're picking these Fourier coefficients from a Gaussian distribution. And the width of the Gaussian distribution, which you can see here, is given from the free theory, from the quantum wave function, essentially. Because you can see that the quantum wave function is Gaussian, right? So we're essentially picking the width of this Gaussian from the width of this free theory Gaussian. So the quantum information is only in the initial conditions and the rest of the evolution is completely classical. Yeah.
Okay, then afterwards it just involves in stochastic ways.
Exactly,
Then,
completely classical. Yeah. Yeah.
Yeah, so okay. I think the stochasticity of the fluctuation may be guaranteed when you consider the background, for example. But do you consider such a case? Or this is more general one?
This is kind of, yeah, just a more general case. We're kind of just working in a flat background for now. Yeah, we were just hoping to work in the simplest case and show kind of a match between the stochastic method and the instanton. But yeah, even again, kind of just a flat background, we're seeing that there's, yeah, not a good matchup here between the instanton and the stochastic, seems like. Yeah.
And is this also is this equivalent to the method where the wave function is this equivalent to compute the time development of the wave function of the scalar fields, for example? No.
Do you mean like it's equivalent to the? Do you mean the
Yeah.
time evolution of the?
So in quantum mechanics, not only the probability distribution, but also the interference effect should be involved in the quantum mechanics. Then such a situation can be taken into account once you consider time development of the wave function, for example. I'm wondering, is this method equivalent to that or not?
I see. I think this method might not be able to capture that kind of behavior necessarily. That's kind of why we just worked in the simplest, in the free theory where we don't really have any interactions. This is just kind of the most basic, m squared, phi squared kind of theory that we worked with. And we wanted to see if it could work in that case. If we introduce interactions, I think we'd probably see even more of a mismatch between the stochastic method and the instanton, because as you said, this method might not be able to capture the information of those interactions. So yeah, I hope that answers your questions. Right.
Thank you very much.
Yeah, thank you so much. Thank you. Thank you so much.
Time is up, so thanks, Neil.
Thank you.
Move to the next talk, and the next speaker is Giuseppe Allaverdi. Are you ready?
Yes.
Yeah, okay. So the title is Super Heavy Dark Matter from String Theory. Okay, please
Let
start.
me share my screen first and open the talk. So can you see the screen fine?
Yeah, yes, I can see the screen.
Okay, thank you very much. I'd like to thank the organizers for putting an excellent program together and also giving me the opportunity to talk. Personally, it's nice to be back in Korea, even if it is virtual. So hopefully we'll be able to resume our in-person meetings soon. This talk is based on a recent work with my former student, Yaksa Oshinsky, who will be in Europe for a postdoc this fall. My collaborator, Michele Ciccoli from Bologna University, and his student, Igor Brockel. So basically, the talk is about the second biggest piece of the cosmic pie. And this is one of the major topics of this workshop. And there are two important questions when it comes to this piece of pie. So one question is, of course, what is the identity of the dark matter and the microscopic origin? But also, an equally important question is that how the relic abundance, the inferred relic abundance, was actually acquired in the early universe. And these questions and their answers have very profound consequences for both particle physics in the form of beyond the standard model and cosmology, basically the thermal history of the early universe. And UV complete descriptions, such as the string constructions, actually, can address both of these in a controlled and consistent way, because not only, they give us beyond the standard model, but also, they can give us an early universe model that describes evolution all the way from inflation to BBN, which is required in order to basically obtain the dark matter relic abundance. So let me go directly to the motivation for our work. And basically, the type 2b flux compactification, there is a typical prediction, and that's the Hubble expansion during inflation to be less than or similar to the gravitino mass. And typically, if you want to obtain the correct amplitude for density perturbations, then the H inflation that is obtained is of some intermediate scale, 10 to the 10, 10 to the 11 GeV. One could try, to build models of low scale inflation, but they are known to have their own fine-tuning problems in general. So in light of this, then the question is how to reconcile. The low energy SUSY, if you want to have low energy SUSY, well, when I say order TeV for the soft masses in the visible sector, not strictly TeV, but maybe 10 TeV or so low in that sense. How to reconcile that with H on inflation of 10 to the 10 to the 11 in light of that relationship. So one way is just to make H inflation much greater than the gravitino mass, and the gravitino mass and M soft to be then close to each other. And that can be done, for example, in KKLT with two exponents, such as in the racetrack model, but this is a rather tuned situation. Another possibility is to basically, keep that relationship between H inflation and gravitino mass, but then have a hierarchy between the gravitino mass and the soft mass in the visible sector, and that's in the sequestered large volume scenarios. But these also require very specific brane configurations and Taylor potential. So now let's say that we want to basically keep that relationship, but then a natural way, to keep that is to make the M soft to be much greater than order TeV. If that's the case, high scale supersymmetry breaking then, I mean, dark matter, I mean, if dark matter is the LSP, it will also be quite heavy. And then, I mean, we seem like to have a problem at the outset. And in a standard thermal history, if you want to just like stick to a standard thermal history, then, I mean, we have thermal production, overproduction of dark matter for such heavy masses, well above like TeV. But fortunately, a string construction generically have an ingredient that can help us. And that's basically, I mean, the point is that, I mean, they also like typically give rise to non-standard thermal histories that involve one or more epochs of early matter domination. And these are like driven by string moduli. And if we consider a simple scenario where we have one modulus that drives early matter domination, then the dark matter abundance basically follows this expression. T reheat is the reheating temperature from the modulus decay, roughly given by this expression. And the branching denotes the branching fraction for modulus decay to dark matter. So the number of dark matter particles per modulus quanta. And this is called the branching scenario. And in this case, you see that the abundance is completely decoupled from the annihilation cross section. So we showed that this scenario can be implemented in general in sequestered LVS, and the volume modulus plays the role of the phi. However, if you want to extend this like to high scale supersymmetry breaking, there are two problems that must first be overcome. So one is that typically the branching fraction for decay to dark matter is like order 10 to the minus 3. And the reason is that in these scenarios, the modulus typically decay, the main decay mode is to 2 gauge fields. And then, I mean, we can like have 3-body decays, including the SUSY particles. And this like branching order 10 to the minus 3 is just a phase space kind of a like factor, like ratio of the 3-body to 2-body. And then we see that if we want to go to like very heavy dark matter, then what we obtain is going to be much, much larger than the observed abundance. And the second point is that typically one also to be careful about producing dark radiation from the direct decay of the modulus. And that's also like a problem that we discussed in this paper. So in order to make this so-called branching scenario work for super heavy dark matter, then I mean, we have like to make sure that first of all, we get a sufficient abundance of dark matter for very large masses. And also we do not produce an excess of dark radiation. Let me first, I mean, describe a general scenario and then a specific model. So here we have 2 scalars, inflaton and the modulus. Inflaton is heavier than dark matter and dark matter is heavier than the modulus. And then the post-inflationary history basically has these main stages. So first we have inflaton oscillations, and then they derive an epoch of early matter domination. Then inflaton decays, and then we enter a radiation-dominated era. And after some time, the modulus dominates. And again, it's a second early matter domination phase driven by the modulus. And then finally, modulus decays, and this is like the final reheating. And then, I mean, this is basically setting the stage for BBN. And since important thing is that since modulus is lighter than the dark matter, then it cannot decay to the dark matter. So there is no direct production. If we combine those 2 early matter dominated stages, then the final dark matter abundance is given by this expression. And here is like the gamma is like the decay rate for inflaton to the visible sector and like a total, and similarly for the phi. And we can also find an expression for the dark radiation abundance. So one thing is that the so-called parameter Wi-Fi, which is the ratio of the initial modulus displacement in Planck units, if it goes up, then the dark matter abundance and the dark radiation abundance, they both decrease. And the main reason is that it's going to be a longer early matter domination, and the entropy injected is going to be larger. So we have a dilution, and that's completely expected. So one thing in general is that if you have 1 or more epochs of early matter domination, then inflationary observables are also affected. And this is the number of e-foldings, right, relevant for observable cosmological perturbations. And these 2 terms are basically the standard ones that appear if you have instant transition to radiation domination. But in general, if we have basically phases where the equation of a state deviate from like W equal 1/3, we have also these other two terms. So this is from inflationary reheating, or basically EMD driven by inflaton, and this is coming from the EMD driven by the modulus. And the point is that now NE will be modified in the presence of early matter domination. For example, here, if we combine both stages, we get this additional term on the right-hand side. And the scalar spectral index is related to NE. For example, in the model I'm going to discuss, also in some well-known models of Starobinsky or Higgs inflation, here, A is equal to 2. And therefore, it means that we have this inequality between the number of E foldings and the minimum number of allowed NS, for example, by Planck data. And it means that NE cannot be too small. So basically, it means that Wi-Fi cannot be too large, because then NE will be too small in light of this inequality. So basically, we have opposite limits from the dark matter abundance and NS. So the model, this is a type 2 model with 3 Kähler moduli. So this is the total volume. This is the tau for the visible sector, and this is the tau for the inflaton. And we have something like Kähler moduli inflation. 2 important parameters are the ratio of this W naught coming from the flux to the volume. And this is much smaller than 1. This is a large volume scenario. And also the ratio of the string the coupling to 8 pi. And in the interest of time, let me just focus on the important things. So this is the modulus mass, and this is the dark matter mass, which is similar to the soft masses, considering that dark matter is the LSP. And basically, since epsilon is much smaller than 1, then modulus mass is indeed much smaller than the dark matter. So dark matter cannot be produced in modulus decay. So it means that modulus decay only dilutes the dark matter abundance. An important ingredient of the model is that inflaton mainly decays to dark radiation in the hidden sector. And then the hidden sector is MSSM-like with a 3 differences. So the lambda, the confinement scale is much higher than the QCD confinement scale. There is R parity violation. And together, basically, they ensure that everything, including the LSP in the hidden sector, basically eventually decays to the lightest particles in the hidden sector, which could be, for example, Goldstone bosons from the confinement, or, for example, the lightest things, in analogy with the observable sector, the electrons. So basically, if hidden electrons are quite light, for example, similar to the visible sector neutrinos, eventually everything, will go, to something which is effectively like a dark radiation. So how much time I have? 2-3 minutes?
Okay, for 2 or 3 minutes for presentation.
Okay, so let me then go quickly. I'll skip the details, but if you have any questions, ask me. I'll come back to these. So the C inflaton coupling to the hidden sector, which is basically this MSS-like hidden sector, actually in the model is much greater than the one to the visible sector as we want. And then eventually we also have the coupling, of the modulus, right, to the visible and the hidden sector, and modulus decay also produces dark radiation. So this is known typically. So this is like a closed, like a bulk closed axion. So let me put all the ingredients together. In this model, we also can compute all these things, and reheating, and from the EMD by modulus and everything else. And in order to get the correct density perturbations, then with this boxed expression must be satisfied. So now what we did is the following. So we impose the requirement from density perturbations, and then also we want to get the correct dark matter abundance, and then we find the dark matter mass. But then we choose these ranges for our underlying parameters, and also the initial displacement of the modulus. So that is typically between this value, as shown in this paper, And either to avoid fine tuning or for the consistency of the construction, we get these ranges for like W naught and GS and lambda that I mentioned. So what we find is like that 72% of like all of these 1,444 points that give the correct density perturbation also give the correct dark matter abundance. And typically for all of these, we get intermediate scale for the dark matter mass of 10 to the 11 GeV. And here, basically, now we go to the W naught and the volume plane and like showing all the points that give the correct density perturbations and dark matter abundance. And just to like, in order to explain the features, that are observed, it's important. It's good like to keep the, like this scaling in mind. So let me skip, but now this is like how these points, right? Basically, how do they match NS? And the black ones are NS within the 2 sigma allowed range of the Planck 2018 results. And the red ones are within the 3 sigma, but outside the 2 sigma. So we don't want to like, go beyond the 3 sigma. So basically, the points, that we like have, that basically satisfy the relic dark matter content as also the density perturbations. They also like match within 3 sigma for sure. The observed value of NS. So I think, I don't have time, so I'm just skipping this, but this is just like to show that basically we also look for a benchmark point that satisfies all the requirements. We also like follow them in a set of Boltzmann equation numerically. So let me just like conclude. So typical situation, if you don't want to like invoke to fine-tuning one type or another, is just like having a high scale of SUSY breaking in string constructions, and that would lead us to think that maybe we have like a difficulty getting the correct dark matter abundance. But fortunately, string constructions also have like another important ingredient, and that is like one or more epochs of early matter domination, and that can help us to get the correct dark matter abundance. And here, I just like mentioned the general scenario and also an explicit model, that can do this. And the interesting thing is that we get like a dark matter mass of intermediate scale about 10 to the 11 GeV. And this is also interesting from another point of view because basically, if dark matter decays, for example, if the R parity is violated, and if it is sufficiently long-lived, dark matter mass like in this range, basically it is close, to that required to explain the recent observations of like high energy neutrinos in Anita and IceCube. And that's a work in progress to see exactly like what we may get from such a scenario. Now I'm done, and thank you for your attention.
Okay, thank you, Roosevelt. And we have question time now. So Takehiro, please.
So is it easy to make modulus much lighter than the gravitational in your scenario?
Yeah, the lightest one, which is like the volume modulus, you can typically make it much lighter than that. There are also some moduli which are like close to gravitational mass or even higher. But those, do not play, an important role cosmologically in this scenario. But in general, you can also have like a scenario when you have, as I have like indicated here, the next to last bullet point here, we can actually have maybe 2 kind of a light moduli compared to the gravitational mass. And then we can have like 2 epochs of modulus domination instead of 1. And that also works. Yeah, so there are some moduli that are lighter than the gravitational mass, and specifically like the volume modulus.
Could you remind us what is W naught? Is it a constant term in the superpotential? But it's written as dimensionless in your.
Yeah, it is. These are all in kind of a Planck units. Yeah. So
so there must be some cancellation to make very small.
So you mean here or where else?
Here, W naught 1 to.
Yeah,
1,000.
So everything is in Planck units.
Oh, 1,000 in Planck units. Is it okay? Very much larger than Planck.
So yeah, okay, we can have one more question. Okay, if not, well, let's move to the next talk and thank Roosevelt. And then
Thank
the
you.
next speaker is So Kano. Are you ready? Okay.
Yeah.
It's
Wait a
when
minute.
meeting offers. Okay, please start.
Okay. Can you see my slide?
Yes, I can see it.
Oh, okay. Thank you. Okay. Thank. Oh, sorry. Okay. Okay. なんか、Okay. Thank you for the introduction. My name is So Kano from Tokyo Institute of Technology. This talk is based on our recent research, which is about the Schwinger effect in inflationary universe. Okay. And sorry. Okay. The message of this talk is that what is a Schwinger preheating? And the Schwinger preheating is the charged particle from the Schwinger effect and dominates the temporarily dominates the universe. And in our work, we find the condition for the Schwinger preheating. This is the message of this talk. Very short. Okay. The table of contents is here. Okay, we first introduced the Schwinger effect. And the Schwinger effect is a non-perturbative pair production from strong electromagnetic fields. The reaction rate of the Schwinger effect is exponentially suppressed by this factor. And m is the mass of the charged particles, and the epsilon is a constant electric field, including electric coupling constant. And when the electric field is larger than square of mass square, the Schwinger effect occurs, and this is called the Schwinger limit. And the Schwinger limit, in case that the charged particle is electrons, and the Schwinger limit becomes 10 to minus 6 Jevs square, and which is 10 to 14 Gauss in magnetic field. It's very, very strong. And the Schwinger effect is still not be observed so far, but in near future, it can be observed by EBR or XFEL or some laser experiments. And the Schwinger effect becomes significant in high energy phenomena, such as heavy ion collisions, the neutron stars, and the charged black holes, and the inflation with electromagnetic fields. In this talk, we focus on the inflation with electromagnetic fields. Sorry. Okay. Oh, sorry. Okay. The motivation to focus on the inflation with electromagnetic field is that this model can be the candidate of the magnetogenesis scenarios. And if the produced magnetic field is helical, we can explain the baryon asymmetry from decaying felicity. And when we consider the second order perturbation of the electromagnetic field, and we can make the quadrupole moment, and this model produces the gravitational waves. And this gravitational wave is observed by the interferometers or CMB observation of pulsar timing array. The full Lagrangian of this system consists of an inflaton component and electromagnetic fields and the charged particles. The ultimate goal of our work is including the magnetic fields and the gravitational waves with the Schwinger effect, and test the model with observation. But this is very difficult. So for the first step to the ultimate goal, and we consider the kinetic coupling model, kinetic coupling electromagnetic field model, and we ignore the inhomogeneity, which means we don't consider the magnetic fields and other fluctuations. Okay. Even though electric field, even though we only consider the electric fields, in general, electric fields during inflation becomes dynamical. So we use the quantum kinetic approach for this dynamical background, which is a procedure to the dynamical Schwinger effect. Okay, so to treat the Schwinger effect, so we show the differences between the full quantum treatment between the quantum kinetic approach. To consider the Schwinger effect, we treat the three processes. One is the pair creation of the charged particles, and the charged particle moving around the electric fields, and the charged particle back react to the electric fields. And in full quantum treatment, we should solve these three processes in quantum mechanics at the same time. But unfortunately, no one can solve them in general electric fields. On the other hand, the quantum kinetic approach, we can treat second of the three processes as the classical mechanics, which is like Boltzmann equations. And this is useful. This approach is useful for the dynamical electric fields. But I remarked that quantum kinetic approach cannot be applied for the inhomogeneous background. So we cannot. So in this talk, we consider the homogeneous electric fields. Okay, let us consider the numerical formulation of the system. We consider the x-directed electric fields and the anisotropic background. This is the Bianchi-1 spacetime, and the alpha is the usual scale factor, and the sigma is anisotropies. And in this background, the Boltzmann equation for the charged particle is written like this. And F is the distribution function for the charged particles, and the epsilon is the electric fields. And these two source terms correspond to the Schwinger production term and the collision term respectively. To perform the numerical calculations, we should specify these source terms. Okay, for simplicity, we approximate the collision term as a restoring force from the thermal equilibrium, which is the Fermi-Dirac distribution. And tau is a relaxation time to the thermal equilibrium. And the Schwinger term is given by the previous research, like this, as follows. And from this Schwinger term, and we obtained, we reproduced the reaction rate same as the constant electric field result. Okay, now we have full equations of the system. Okay, very long, sorry. And this is the Friedmann equations, and these correspond to the equation of motion of anisotropies and inflatons and electric fields. And these three equations are induced from the Boltzmann equations, where we introduce the moments of distribution function and consider the hydrodynamic approach with closure conditions. And let me explain the differences between the conductive current and the polarization current. Conductive current here is a usual current of the charged particles defined by the energy momentum tensors. On the other hand, polarization current is an induced current from the Schwinger effect, and the representation is here. Okay, this is the differences between the conductive current and the polarization current. Okay, to perform the numerical estimations, we should specify the inflation model. Okay, in the previous research, they consider the Starobinsky potential and the Rattler kinetic coupling model. And in this, by using this inflation model, we obtain the time evolution of the system. And this graph denotes the time evolution of the energy density of each component. The vertical line is the energy density, and the horizontal line is the cosmological time. And the black dashed line denotes the inflation end. And the red, blue, orange, green line represent the electric fields and charged particles and the infraton and the total energy densities. And here we find that there is a back-reacted phase from electric fields to infratons. And after the inflation ends, we find that charged particles dominate the universe here. This is the Schwinger preheating. But Schwinger preheating does not always occur. So in case of, we consider the anisotropic inflation. So we obtained the similar figure, which represents the time evolution of the energy density of each component. And we also find the back-reactive phase, but after the inflation end, we find that preheating does not occur. So we have a question that when does the Schwinger preheating occur? And what is the condition for the Schwinger preheating? Then the answer in the numerical side is solved by considering these two graphs. These two graphs denote the relation between the maximum value of the energy fraction of the charged particle and the coupling constant. Here in the left-hand side, and the Schwinger preheating occurs when the energy when the coupling function is larger than almost 8. In this case, the Stravinsky potential and the electromagnetic coupling cause the Schwinger preheating. On the other hand, the anisotropic inflation model, the Schwinger preheating does not occur. So this is the numerical answer to the question. So we also have a question that what is the analytical condition for the Schwinger preheating? Okay. From the next slide, we consider the analytical conditions. Okay. The Schwinger preheating is occur when the Schwinger preheating occur when the charged particles dominate the universe, and the charged particle receives energy from the electric fields via the Schwinger effect. Thus, the necessary condition for the Schwinger preheating is the electric fields dominate the universe. So to consider the Schwinger preheating, we somehow analytically treat electric fields during inflation. But in fact, we expect that there exists an attractor solution of electric fields. And this is because the infraton gives the kinetic energy to electric fields through the kinetic functions, and at the same time, electric fields gives a negative feedback on the infraton. So we can expect that there exists an attractor solution for electric fields. In our paper, we derived the attractor solution by model-independent way as follows. This representation does not depend on the inflation model. And by using this attractor solution, we obtain these two graphs. These represent the energy time evolution of the energy fraction of electric fields. And the horizontal line denotes the E-folding number, and the 0 denotes the inflation end. And the blue line and the orange line denotes the numerical result of the electric fields and the attractor solutions. In the both panel, attractor solution well approximates the numerical result. So to consider the condition Schwinger preheating, we can use attractor solution, and it can be seen that we can use attractor solution to consider the Schwinger preheating. But however, in case of lateral coupling, and the attractor solution always dominates the universe at the inflation end. So we cannot use a necessary condition here to determine the Schwinger preheating. But we know the case that electric field cannot enter the attractor solution when beta is small. We give the example of this case. When we consider the 7.7 coupling constant, okay, this is a time evolution of the system, and please focus on the electric red line and the gray line. Red line denotes the electric field, and the gray line denotes the attractor solutions. And that black dashed line is inflation end, and at this point, electric field does not enter the attractor. So we have a new necessary condition to the Schwinger preheating. To cause the Schwinger preheating, electric field enter the attractor before inflation end. Okay, we use this necessary condition to consider the Schwinger preheating. Okay, let us use the slow roll solution. Slow roll solution, low SR. Low SR is given by ignoring the back reaction from the charged particles, and we find the intersection of the low slow roll solution and attractor solution. At the intersection, slow roll solution exceeds the attractor solutions. Okay, and we obtain the relation between intersection and coupling constant. The black dashed line represents the value of phi, and phi satisfying the epsilon v equal 1, 0.3, 0.1 from bottom to up. The black dashed line, each black dashed line cross the blue lines and at 6.6 and 7.6 and 9.4. This can be the lower bound of the beta. But there is an ambiguity for intersection because slow roll approximation is invalid at the end of inflation. Thus, we cannot determine which value is a precise lower bound of coupling constant. However, comparing with numerical results, our work well explains the condition for the Schwinger preheating. Okay, let us summarize our work. Okay, and Schwinger preheating is charged particles induced via the Schwinger effect temporarily dominates the universe. And in our work, we numerically and analytically find the condition for the Schwinger preheating. And in future work, we introduce the perturbative decay of inflaton and the magnetic field and the gravitational waves. That's all.
Okay, thank you. Okay, so now we have question time. So, any question? So maybe we don't have any question. So okay. So thanks so. So and we move to the final talk of this session. So the final talk is by Takumi Hayashi. So are you ready?
Okay.
Okay.
Can you see my screen? Okay.
The title is Vacuum Decay in Digital Space-Time with the Lorentzian Path Integral. Okay.
Thank you very much for introduction. I'm Takumi Hayashi, belong to the Research Center of the Early Universe in Tokyo University. And today I'd like to talk about the vacuum decay with Lorentzian path integral in the zeta space-time. And okay, sorry. Okay, then let me introduce the background of our work. We consider the vacuum decay, which is predicted by the quantum field theory.
Sorry, we do not see the
We still see your title page.
Oh, really? Mhm. So, excuse me, can you see the next page? Introduction
No.
page?
No,
No.
we still see the title page.
I don't know. Sorry.
一旦共有を解除してみて。
Okay. Excuse me. Then maybe I can use the PDF for. Okay, then I will try again. Can you see the next page? Introduction page? No?
I just see the black screen.
Okay, then I will use a PDF. Sorry for okay. Okay, then can you see my screen? PDF?
No, we still see the black screen.
Okay. Okay, then. Can you see my video?
Yeah, well, I see your face, but
Can you see my video? I'm talking in blue. Can you see my video?
Yes.
Yes, but
perhaps it would be better for you to the sharing your display itself, not the file.
Okay. Thank you for. Can you see my display?
Not yet.
Completely black?
We just see the completely black screen.
Okay. What happened? Is it any procedure to give presentation? For example, the allowance of
well,
Oh. Okay. I will reset the Zoom. So excuse me for leaving for a while.
Okay.
Okay.
Well, we again see the, yeah, okay, maybe it
Okay,
works.
so now we see the introduction page, so it's good. It
Ah,
looks
okay.
good.
Sorry, I'm extremely sorry for bothering you. Okay, then let's start again. Okay. Okay, and then okay, I will talk about the vacuum decay in this talk. And yes, okay, then vacuum decay is the phenomena predicted by the quantum field theory. You have if you have a scalar field with the metastable vacuum, the quantum tunneling from false vacuum to true vacuum will take place. And such kind of phenomena is ubiquitous. The most famous example is the Higgs instability in standard model. The quantic coupling of the Higgs field become negative at high energy, so you have a true vacuum at here. And there is many UV theory which has multiple scalar fields, and the complicated potential shape could have many metastable vacuum. So considering such kind of quantum tunneling is very motivated. And after the nucleation of the true vacuum bubble, then the bubble expand into the universe, and such bubble nucleation could induce rich phenomenology such as gravitational wave production sourced by the energy density, and PBH production sourced by the energy fluctuation on the or the particle creation coupled to the tunneling scalar field. Then the vacuum decay is intensively studied for so far, and the most the well-known way to deal with the vacuum decay is the Euclidean path integral. You can characterize the vacuum decay rate or probability as a Euclidean path integral, and you can approximate it as an action of the bounce solution. Yes, here B is a bounce action, and this depends on the notion of the imaginary part of the energy. But in some situation, this notion is very ambiguous. For example, the in curved spacetime, you have no unique notion of the energy, or for dynamical gravity, you have a Hamiltonian constraint which constrain the energy to be zero. So the notion of the imaginary part of the energy is very ambiguous. And furthermore, the bubble nucleation with larger or smaller bubble than the critical value, which is the predicted by the Euclidean theory, is not calculated in the such kind of treatment. So these reasons tempt us to study the dynamically evaluate the Lorentzian path integral. Okay, then before going to that, let me introduce the symbol approximation of the original theory. The potential of the scalar field is can be characterized by the sigma bubble wall tension and the bulk energy density delta V. Then the situation is like this. The bubble wall is on this world sheet with the energy density sigma and some bulk energy density delta V. And then the origin action can be decomposed into the world sheet contribution and bulk contribution. And here we consider the bulk spacetime is a dot-zeta spacetime. And x mu is embedding into the bulk spacetime of the world sheet. And imposing the symmetry on it, we have just the dynamical value as a R as a dynamical value here. This is a schematic picture. Then this is a Euclidean theory, and we can calculate the bounce equation and bounce action. Then we have a radius and of the bubble and the bounce action. This result is same as a one predicted by the original field theory, so we can successfully truncate it. Then let's go to the Lorentz path integral. In order to canonically quantize the theory, we introduced the modified type of the potential action. This is a quadratic action proposed by the Polyakov, which is frequently used in the string theory or something. And then here we introduce a metric on the worldsheet, which is not relevant to the bulk spacetime. But on-shell equation for gamma AB gives this connection between the metric on worldsheet and induced metric. So it can describe the original Nambu-Goto type action. And we consider digital spacetime and imposing symmetry. We can reduce the degrees of freedom to these three dynamical variable. And we have a gauge symmetry for timely parameterization symmetry. So we can gauge fix to constant n. Then the path integral for these all variable is written in like this. And this is a schematic picture. The bubble wall you can start from the force vacuum with radius 0 and make a quantum transition to some finite radius R1. And this quantum amplitude is given by this expression. And approximate it in the on-shell classical solution for T and R. Then you have a single integral expression of the transition amplitude. This is simple, but difficult to evaluate because the integrand is pure phase, so frequently very oscillatory. So let me introduce the technique to deal with such kind of oscillatory integral. If you have an original integral here, and analytically continuate this effective action to complex plane, and change the contour to the C. C is the steepest descent contour of real part of the exponent. By the analyticity of the this effective action, we have a very good feature that the imaginary part of this action, this exponent, is stationary. So integration over this steepest descent contour is no longer oscillatory, so we can approximate it as a saddle point method. And this is a very famous example. The Airy function is defined in terms of the integral over this original contour, but you can you analytically continuate and find saddle point. Here we have two saddle points, but the relevant one is this above one because the steepest ascent contour intersect with the original one at once. So we should take this contour. On the other hand, this saddle point has a steepest ascent contour which does not intersect with the original one, so we should not care about that. Then we pick up this saddle and perform Gaussian integral. Then we have such expression, asymptotic expression. This is very famous. Okay, let's use this technique to evaluate the effective potential for the our model transition amplitude for the bubble wall. Then effective action is calculated by this action, and T and R is a classical one. So we solve the equation motion with a boundary condition. Here, the resultant nucleated bubble radius is RB, which is equal to the value of the value predicted by the Euclidean theory. Then the action become a relatively simple form, and integration over real axis can be deformed to the this steepest descent contour passing through the saddle point. So picking up this saddle point, we have such kind of expression, and this exponent is the half of the bounce action. So after absolute squaring of it, we have such kind of expression e2 minus b, and it is inconsistent with the prediction by the Euclidean theory. So our method to formulate the bubble nucleation is consistent and verified with such kind of comparing. Okay, then let's go to the larger bubble nucleation. I change the boundary condition for the R, dynamical value R, to the larger than the original Euclidean bubble radius. Then the bubble nucleation, then the action is relatively complicated, but and you have some branch cut here or some singular point, but you don't need to care about that. There is a saddle point here, and passing through the saddle point, there is a deformed steep descent contour. So we pick up this saddle point to evaluate the transition amplitude. Then you have additional pure phase rotation in the expression. So after absolute squaring of it, you have a same exponential factor for the probability. So the result is that the probability for large bubble nucleation is same as the probability of creating critical size bubble. And this pure phase rotation indicate that the such kind of large bubble nucleation process is can be decomposed into the critical bubble nucleation and expansion to the large bubble. Okay. Then let's go to the small bubble nucleation case. And we consider such kind of boundary condition. R1 is smaller than R0, RB. This is a Euclidean value. And we have such kind of analytic behavior. And you have a saddle point here. So you can evaluate it by the picking up this saddle. Then you find the positive real correction to the exponentiate. So the probability of finding the smaller bubble is much larger than the finding a critical bubble. But this is very intuitive result because let's see this effective potential for the bubble radius. This is a bubble potential wall, and the wave function exponentially decrease when passing through this potential wall. So the finding the smaller bubble, the probability of finding smaller bubble is much larger than the finding the critical bubble or large bubble. Okay, then, but this small bubble is not considered as a classical bubble because the classical small bubble has a positive energy, but the initial state is zero energy force vacuum. So we can't consider that we can't expect that the such kind of transition. So we should interpret this small bubble as some position eigenstate rather than the some coherent state which describes the classical small bubble. Okay. Then let me summarize our result. We formulate vacuum decay in Lorentzian path integral in Dirichlet spacetime instead of Euclidean method, and provide the direct interpretation of the vacuum decay as a transition of bubble wall. And we find a consistent probability for bubble nucleation with Euclidean analysis, which guarantee our correctness of our method. And we consider and we calculate the large bubble nucleation and small bubble nucleation, which cannot be calculated in the Euclidean analysis, and find that large bubble nucleation probability of large bubble nucleation is same as a critical one, and we can interpret it it's a nucleation plus some classical expansion. And a small bubble gives a large probability to find. Okay, then that's it. So excuse me for bothering the giving a presentation. Thank you.
Thank you, Takumi. And so the time for the question. So probably, yeah, okay, so we don't have any question. So let me finish this session, and I thank all speakers, and well, we will meet again in the afternoon session.